Now here we have almost the same situation, but now I'm saying this wheel has mass. It has a mass of 77 grams. We're going to approximate it to be a disk, and because it's a disk, its moment of inertia is 1/2 m r squared. 1/2 m r squared. I'm going to make these capital letters instead. All right. Typically we use capital letters when we're talking about the radius and mass of an object, and we use lowercase ones when we're talking about a point mass. That'll be our convention. Now conceptually, pretty much the same thing is going on here. We can still say that our KE naught plus PE naught equals KE final plus PE final. We can again say that's 0. We can again say that's 0. Our PE naught is still MGH, but our KE final now has two parts. We've got 1/2 the mass of the block times the velocity of the block squared. We also have a rotational kinetic energy coming from the pulley. So almost exactly the same thing is going on here, but that energy is being distributed to two different places. Now right away, if we think about this conceptually, versus our last scenario where the pulley was massless, we can see that the block isn't going to be moving as fast anymore because now some of the energy is going into accelerating the block downward, but some of the energy is also is increasing the kinetic energy of the disk. So because that same amount of potential energy is being split up into two places, then we can see that the translational kinetic energy, the 1/2 mv squared, is going to be a little bit less. Right. So now let's take a look. This is mass of the block as well. And we can start plugging stuff in. Mass of the block, still 1.1, g, 9.8, height, 0.98, half is a half, mass of the block, 1.1. Now, this causes a, it might not seem like it, the scenario is different, but we can still use that same relationship between the velocity of the block and the angular velocity of the wheel, because as the block rolls down, it is still unspooling that rope and spinning the pulley at the same rate as the block moves down. So we can still call this an omega times radius of our pulley squared. Then we just have our 1/2 I omega squared, and I is 1/2 mass of the pulley times the radius of the pulley squared times omega pulley also squared. So once again we can get the angular velocity of the pulley. It's just that now that potential energy is going into two different places. It's giving the block translational kinetic energy, and it's giving the disc, the wheel, the pulley, whatever you want to call it, a rotational kinetic energy. Here we're looking at another example of our mechanical energy being conserved. We've got an object rolling down a hill, has mass m, radius r, it's h off the ground, and it rolls without slipping. Remember, rolling without slipping is the condition under which we can utilize the relationship that velocity is equal to omega times r. So your task here is to put in order which would hit the bottom first. We've got a hollow sphere, solid cylinder, solid cylinder. Now, clearly what's different about these four objects is their shape, and because their shape is different, their moments of inertia are also different. Right? So if we looking at our table from the book, a hollow sphere has a moment of inertia of 2/3 mr squared. A solid sphere has a moment of inertia of 2/5 mr squared. Hollow cylinder, we have a moment of inertia of mr squared. The book calls that a cylindrical shell. And a solid cylinder, we have a moment of inertia of 1/2 mr squared. So we can see that the moment of inertia of the hollow cylinder is the greatest, followed by the moment of inertia of the hollow sphere, and then the solid cylinder, and then the solid cylinder, and then the solid sphere. So I think it's pretty obvious that the order that they'll hit the bottom in is either going to be solid sphere, solid cylinder, hollow sphere, hollow cylinder, or the other direction, hollow sphere, hollow cylinder, solid sphere, solid cylinder. I said those backwards, whatever. Obviously, we're not going to jump around in this order. So let's look at the math. Well, in all of these cases, we have our initial potential energy is turning into our final kinetic energy, which is translational plus rotational. In each case, our initial potential energy is mgh. Sorry, I called that a capital M. Our kinetic energy is going to be 1/2 mv squared, and our rotational kinetic energy is going to be 1/2 I omega squared. Now, using the fact that this is rolling without slipping, we can change that omega to be a v over r. Right. And what's important is that v, because the one that hits the bottom first is obviously going to be the one that has the highest velocity. So let's do some algebra here. If we want to get that v by itself, say mgh is equal to v squared times 1/2 m plus 1/2 I over r squared. So our velocity is going to be equal to the square root of mgh over 1/2 m plus I over r squared. Now remember, all of these things are the same except for the moment of inertia. And since the moment of inertia is being added to the denominator here, that means that a greater moment of inertia will result in a smaller velocity. So we can say that the velocity, the greatest moment of inertia was the hollow cylinder, so the velocity of the hollow cylinder is going to be less than velocity of the hollow sphere, which will be less than velocity of the solid cylinder, which will in turn be less than the velocity of the solid sphere. So the solid sphere, our solid sphere will be number 1, our solid cylinder, number 2, our hollow sphere, or hollow, sorry, hollow sphere will be number 3, and our hollow cylinder will be number 4. So while all of them have the same kinetic energy when they reach the bottom of the hill, because they had the same initial potential energy and no energy is lost, they don't reach the ground the same rate. Some of them will have, well, we figured this out. The solid sphere will have the greatest translational velocity, greatest translational kinetic energy, which means that it will have the least rotational kinetic energy, and so on down the line.